Okay, this is chapter 17. It's about powder metallurgy processes, and in this case, in this process, as the name implies, we are using powders of different materials, and mostly we perform these processes on metals. In this chapter, we'll be discussing the details of these processes and mention about some equipment related to this study. And with such powder metallurgy process, we can manufacture mostly smaller parts, high number of smaller parts like rings, gears, cams, bushings. But obviously, if you have proper equipment and required powders, you can even produce longer, maybe much more complicated product. But mostly, it's preferred for small in size but high in number products. So what we are doing in this basic process, as the name implies, as I said, we are using powders, metal powders. We put them into a kind of a die. We compact them. Depending on the complexity of the die, the resulting shapes may have higher geometric complexity. And later, after this compaction is over, we take this part out and do extra operations like sintering. With the help of it, the strength of the part is increased. And lastly, if it's required, you may do some extra secondary operations. And the advantages is that we have different types of metal powders available in the market. You can use any kind of metals. Even you can mix some metal powders, do some alloying, and try to obtain various properties. Another advantage is that with the help of this process, we obtain net shapes, not near net shape, but net shapes can be obtained. So if the surface quality is fine for you, then you don't need to do extra operations. Another thing, it's not actually highly expensive. If you have the power, the required size of powders, metal powders, then the rest is not highly complicated. But if the shape of your part is somehow complicated, then you may consider other operations like casting maybe or machining, depending again on the complexity. The other advantage, while you are mixing the powders, while you are doing some compaction, you can even embed some amount of oil inside your part. So with the help of them, your parts, for instance, your bushings, your cams, your gears may be self-lubricating. So once you have such oil inside, then during the operations, the users will not need actually adding extra oil around. So that's a nice advantage, and it increases the service life. These are some typical parts, as you see, manufactured with the help of powder metallurgy. And if you remember, while we were discussing the tool materials, we said that most of the tools are actually manufactured with the help of powder metallurgy. And they have the powders of tungsten carbide, other types of materials, put them into a kind of an die, apply pressure, and obtain such tools. And these are highly stronger. If you remember, we do machining with the help of these. So what are the formal stages of actually powder metallurgy? First of all, we need to manufacture the powders. It's quite difficult. There are different ways. We'll be discussing some of them. After you have the powders, what do? You do some kind of mixing. You put them into a kind of a chamber, mix them, and then pour them into a die, apply pressure, compact them, obtain a green part. After the third stage, you got the green part. Since the strength is not high, people call it as a green product. And later, we do sintering so that there will be more solid connection between the powders. And with the help of it, with the help of sintering, the strength, the density is improved. And if the quality and the other properties are fine for you, you may be done with fourth step. But if you want to have actually better surface quality or better strength, better densities, then you may go with some other finishing or secondary operations. Now we'll discuss all these steps one by one. Let's have a look at the first one, how we manufacture these powders. There are different ways, but the most atomization. I will talk about them in a moment, but I forgot to discuss the sketch here. This is showing the pipeline of powder metallurgy. We prepare the powders with different methods: atomization, reduction, comminution, mechanical alloying. Once you have the powders, then you may add some additives like some chemicals so that the powders will be fused together, joined together easily. And we do blending, we mix them so that we have a uniform mixture. And later we do compaction, and that can be done at room temperature or high temperatures, depending again on the application you're going to use your part. Later, if it's not done actually hot temperature at hot temperatures, you need to do further sintering. And lastly, as we discussed, if you are not satisfied, you may go with some extra operations like coining, forging, machining, some extra heat treating, impregnation. This is adding oil, infiltration. This is actually embedding different materials, different metals into the product. And lastly, you may cover the surface of these parts. Now let's go back to the production of powders. I said that there are different ways, but the most popular one is atomization. And in atomization, there are again different ways to do it. So what we do, we start with liquid metal stream. So we need to apply obviously some heat, increase the temperature for our metal so that it's in the form of liquid, in the state of liquid. And then later what we do, we apply some pressure and try to move it through a small orifice. And while it's moving through that, it's actually broken into some little dots, little particles with the help of sometimes some gas, inert gases, or if it's then water atomization, we make use of water to actually divide this molten metal into smaller products. And then later, the temperature decreases and we obtain these metal powders. You can see there are different atomization methods. The first one, gas atomization. The second one, water atomization. The third one, centrifugal atomization. We make use of the centrifugal force. You see metal, liquid metal is poured into that ton dish, and then we have liquid metal here. Once it actually hits this spanning disc, due to the centrifugal forces, these little particles are spread away and they are actually, their state is changed into solid, and we have these powders. But obviously this is quite difficult and we cannot easily maintain the uniformity of the powders. And in this powder production, the main thing is actually to obtain as uniform as possible metal powders. Since if you have, let's say, 10 micrometers of powder and 100 micrometers of powder together, it's quite challenging since you need to do extra screening operations. You need to divide them into some groups, and then later you may use them in your actual sintering operations. And in the first one, as we discussed, we are using inert gases. So with the help of these inert gases, the liquid metal is actually divided into little products, and then later, once they are solidified, they are collected underneath this chamber. And it's the same in water atomization. The only difference, we are making use of high pressurized water instead of gas, but the rest is the same. And also, obviously, we have extra water. We need to remove it and try just to have the powders in this process. And the last one is actually by using a consumable electrode. This is our electrode here. You see, by having some maybe contact, we actually remove little parts from this consumable electrode. But this is again quite difficult. The easiest way is to use inert gas. The first one is the most frequently utilized approach. And you can see some different types of powders obtained. The first one is actually iron, and this one's again obtained by atomization. And it's not actually, as you see, not circular, not sphere. It's quite irregular. But if you look at the case where we use electrode, rotating electrode, the difficult one, we have muchly more sphere actually products, and their size are larger than the size of these particles in atomization. So there are different ways, and depending again on the application you are going to use these powders, you should select the right type of atomization methods. And we further have different methods like crushing these parts by using rollers, some other ways like ball milling or hammer milling. But as I said, the most frequently used one is atomization. So now what we have done, we have manufactured the powders, and then in the second stage, we are going to mix these powders. We are going to blend them by using maybe some extra chemicals, some lubricants, maybe some additives, so that in the other stages, in the upcoming stages, things will be much easier. But the main function, main aim in blending operation is to obtain a uniform mixture. Since we may be using one type, two types of, three types of metals maybe. So if you don't mix them, then in one part of your chamber, you may have, let's say, iron. In the other part, you may have copper. But if you do blending, that will be a nice approach, since you have uniform mixture, and that will be actually the desired thing, since in the resulting part, we don't want to have actually different properties in different parts of the object. We want to have actually uniform properties, so this is only possible with the uniform mixture of these powders along with some lubricants and some additives. And another advantage of actual lubricants is to decrease the friction between these metal particles. And furthermore, with the help of these lubricants, the flow of this metal powder is improved so that they can easily fill some gaps inside your die. Now we have done with the two stages. The third stage is actually pressing, compacting these metal powders. So how we do it? We pour, actually, let me show you a kind of a sketch here. Yep. This is our die opening, by the way. What we do, we feed our powders into this opening and then apply pressure with type of punch. And then this is an ejector. We move our green part, green compact. This is the strength of this part is not high. You may even break it with your hand. So that's why it's called as green part. And this is the compaction stage. And later we do sintering. Now let's go back to the descriptions here. So these are the purposes. We want to obtain actually the desired shape. Since we have a die, we pour powders into it, and with the help of compaction, the shape is obtained. And in that shape, obviously we need to have particle-to-particle contact. The powders should be touching each other. Another thing we want to do actually with this compaction process, that the parts should have actually kind of enough strength for the upcoming operations. If your compaction is not proper, then even you cannot remove that part from the shape, from your die. It should have required strength, but not too much. And this can be done by using simple mechanical presses, hydraulic presses, it doesn't matter. But obviously, at the end of this compaction, the strength of the parts will be lower. And the density of the green compact obviously depends on the pressure you're applying. And whether, regardless of your actually compaction pressure, you will always have some porosity inside your resulting part. And theoretically, the maximum is about 24%, since if you use perfect spheres, you'll have some porous region in between, and that is corresponding to 24% of the whole volume. And in order to decrease actually porosity, we have some different ways. People may sometimes use smaller, let's say, powders, smaller powders inside of larger powders, so that the smaller ones will fill the gaps between the larger powders. And you can see the effect of compaction pressure. Actually, as you see, we cannot reach to 100%, but obviously if you continue increasing the pressure, the density will be increasing to some levels, but maybe about 95%, but not more than that. And we have another issue regarding this compaction. It's better actually we do it as uniform as possible, since if you just, for instance, if you look at this case here and have a single punch and apply this punch from the above, what will happen? You'll have different densities. You see, it's to the bottom part, the density is decreased. But if you use a dual action, this time you have similar densities at the bottom and at the upper portion, but lower densities at the intermediate region. And for complicated shapes, obviously, one or two punches may not be enough. You may need to use extra punches, like in this case, called as multi-action. And since we have a kind of a stair here, a shoulder here, So for each part, we have one bottom part. And with the help of it, as you see, we have almost the same color throughout our shape cross section, which means that we almost obtain uniform density on this part. But if you look at here, if you use a single action punch, then you have less density here, but higher density on this side, since obviously the thickness is there a bit lower. Since the thickness is high on the left-hand side, its density is lower. And why density is important? Since if you increase density, then probably the strength and elastic modulus of your resulting part will be improved. For that purpose, if the curved part is highly critical for you, then you should design these punches, your equipment, properly. And you may further do actually some isostatic type of pressing. For that, you need to have some special, maybe higher powerful equipment presses. If you do it at room temperature, it's called as cold isostatic pressing, but this is not frequently used. Instead, we mostly use hot isostatic pressing. Since with the help of hot isostatic pressing, we obtain almost 100% density, which is very close to the values of casting process. And this is mostly utilized for the products actually which are to be used in critical applications like aircraft or aerospace applications. People mostly go with hot isostatic pressing. And for the cold one, this is actually the case how we apply this presses, isostatic presses on it. For that purpose, we need to have such a special equipment, and we need to have fluid inside. And again, as in the case of some fluid hydroforming processes, we have a rubber in between the powders and the fluid. So once you increase the pressure, then these powders will be actually undergoing some triaxial compressive stresses, and the density will be improved furthermore compared to the ordinary compaction processes. But the thing is that if you are doing hot or cold isostatic processing, the complexity of your shape cannot be too much. But with some other ones, you may be going with higher complexity, but it is the lowest for the hot isostatic pressing. So if you are going to do hot isostatic pressing, then you should have much simpler products. You're not responsible from these parts, these subsections, but I will be now discussing the sintering part, the fourth stage of powder metallurgy. So in sintering, now we have the green part after the compaction operation, but the problem is that its strength is not too much and it's quite brittle. You can even, as I mentioned, break it with your hand. So what we need to do, we need to join these powders more firmly so that this can be used in maybe under high loads, under critical applications. So what we do sintering. In the sintering, we simply heat this green compact to the temperatures which is below the melting point of the metal. If it's higher than that, what will happen? We cannot retain the shape. So that's an important issue. The temperature should be below about maybe 70%, maybe 80% is written here. It shouldn't be more than that. Otherwise, the shape of your metal, the shape of your part will be modified. There are some typical sintering temperatures for different metals. Usually for stainless steel is quite high. For ferrites, for tungsten carbide, the sintering temperatures are quite high. And the time is also important in sintering, since if you keep this temperature the same but increase the time, again, you cannot control the shape, since you will be giving too much heat and probably your metal, your part will be deforming, and you will have deformed surface. The overall quality will be decreased. So how sintering happens? There are different ways. We have diffusion type, vapor phase transfer, liquid phase sintering, and the most popular one is diffusion mechanism. It's also called as solid state bonding. You can see the fundamentals of solid state bonding or diffusion mechanism here. Both powders are actually trying to decrease their free energy, and this free energy is decreased with the help of a decrease in the surface area. So how surface area decreases? If these parts are joined together. As you see, a neck forms here, and if the process continues, the size of the neck increases and the total area of this couple decreases, which means that their free energy is decreased. They are a single part. But the difficulty is that in these sintering processes, the overall size of your part is decreasing. We have shrinkage, and you should be aware of this shrinkage value and then design your dies accordingly. You should have larger dies than the desired dimensions, so that once you have shrinkage, you will have the desired shape, desired values. And we have vapor phase transfer. This is done at very high temperatures, almost close to the melting point temperature, but quite difficult to perform. Or we have liquid phase sintering. In that case, we make use of some additives. As you see, these additives are having lower melting point temperatures. Due to that, even though your blue powders are not melted, these gray ones are melted and they fill all these cavities. So you will have, again, 100% density or no porosity. And the problem is that obviously the strength of this part will be quite lower compared to the part having all the filled with blue powders just. But if you have blue and gray powders together or additives, then its strength will be lower compared to the fully blue case. And we also have spark sintering. This is, again, highly difficult, but the advantage is that you can simply do this sintering and compaction at a time. As the name implies, we have a kind of actually apply current, and we apply some sparks. With the help of this discharge, electrical discharge, the powders are melted and joined together. As I said, this is quite difficult to implement. So now we are actually, we may be fine with the result of sintering operation, but as I said, there might be some problems like the surface irregularities, the roughness may be quite high. So what you need to do, you may apply some extra operations. These are called as secondary or finishing operations. What are they? You may do coining or sizing. It's very similar to the forging operation we discussed, the coining operation. Obviously, this one increases the dimensional accuracy. Or you may do some extra sintering and do some hot forging. Again, the dimensional accuracy will be improved. Later, or as an alternative to the first two, you may do machining, grinding, plating, heat treating. So they will have different advantages. For instance, with machining, you may change the geometric properties of your part. With grinding, you increase the dimensional accuracy, surface quality. With plating, obviously, the appearance changes, and you may increase the life of your part by applying some special coating, which is actually highly resistant to corrosion. Further, you may do extra heat treating. With the help of it, the overall strength and hardness may be improved. Then we have two different processes. The first one is called impregnating or impregnation. By impregnating, what do? You embed some oil, maybe about, as you see here, 30%, it's 10%, 20%. As I said at the beginning, with the help of this impregnation, you can obtain self-lubricating products, and these are highly useful. They improve your service life without actually looking at your machine. The same machine can run for a longer time. Then we have infiltration. This is somehow similar to the previous one, but the main difference is that instead of adding oil in between the powders, we are adding different metal, metal which has actually a lower melting point than the original powder. So how we do it? We make use of the actually capillary reaction of these metals or the powders. So once you increase the temperature to the temperatures above the melting point of the secondary material, then what will happen? This secondary material will be in liquid state, but our original powders will be in solid state. So later, due to the, again, capillary reaction, the secondary material will fill all the cavities, and you will be increasing the overall density and overall mechanical properties like the hardness of your part. And then later we do electroplating. It's another option for post-processing. And lastly, you may use roll densification or extra densification. As the name implies, with the help of these special equipment, we are increasing the overall density of the part. And as you have seen, the equipment, the dies, the design of the dies, punches are highly important since they determine the overall shape. So if you are trying to manufacture complicated ones, then you should spend some more time on the design of your die and the punches. So you see even such shapes can be obtained, but you should be careful about the sharp radius. These are quite difficult to obtain. It's better you go with some smooth, let's say, corners. So let's briefly talk about the economics of powder metallurgy. As I said at the beginning, with this process, we mostly obtain net shape, but depending on your requirements, you may not be satisfied. And if that is the case, we can say that this is near net shape. So if it's near net shape, then what we do, we apply some extra finishing or secondary operation. But for net shape operations, it's highly economical, especially for medium size or maybe for mass production. It can be even competitive with some casting, forging, and other machining operations. And this is all, I think, all for this chapter. Make sure that, again, you have a look at these review questions and qualitative problems.